So my observation for this video is that lines are nice. We like them. We like them a lot. We wish all functions were lines because they have really great properties. We've learned how to work with lines forever. I mean, all the way back in like Algebra 1 and maybe even before that. They have the same nice slope everywhere. And that's kind of what makes them nice and regular here. And on top of that, the slope tends to have interesting meaning depending on what the function actually is, what it actually represents. So for example, you're going for a jog and you graph the amount of distance you travel as a function of time, then by now you guys know that the rise over run is the amount of distance traveled divided by time. It's your speed or your velocity. And the fact that that slope is positive means you're always running forward, right? So the slope of the line is equal to the velocity. So the slope tends to have interesting meaning. It has meaning that's relevant to the problem at hand, to the physical situation. And the fact that we have constant slope everywhere, the same slope everywhere, means that you're jogging at a constant pace. Of course, this isn't completely realistic, right? Ordinarily, if you're going off on a random jog, sometimes you'll slow down a little, sometimes you'll speed up a little bit. So you might have a function like this. Now this is kind of it's best not to interpret this as the graph of somebody jogging, because it means that they started a negative distance and then they moved forward for a while, they stopped, they came back, they ran back in the other direction and stuff. So this would be awkward. But it still kind of raises the same interesting question. How do we handle, what do we mean when we talk about the slope of a nonlinear function like this? And just in general, with linear functions, we have a whole basic algebraic theory to deal with these guys. How on earth are we going to say anything about these complicated nonlinear functions? Well, a mathematician always likes to take a problem that's complicated, one he does not know how to solve, and try and change it some way or another into a problem that he does know how to solve. So I wish this was a linear function. And you know what? The basic spirit of it is this. Here's really in many ways, here's the point of differential calculus. You see, you pick your favorite point, like that red point I drew right there. The x-coordinate is a, so of course, since this is the graph of the function f of x, the y-coordinate should be f of a. So that's the point a, f of a, right? And suppose I zoom in on it. More, and more, and more, until my Surface Pro cannot zoom in anymore. One note. So what ends up happening is, it started to look more and more linear. So since I can't actually do that, let me kind of show you what it would look like if I could do that. So if I maybe draw this little box and I zoom in, here's what the function would look like. Okay, maybe I don't like that enough. Maybe I want to zoom in even more around that point. And then it would look something like that. So one thing you should notice is that it's looking more and more linear as we zoom around this particular point. Okay, so that sounds really great because we loved linear functions, right? We spent the beginning of this video talking about how much, and reciting a nice little poem, how much we love them. So here it looks really good when we can zoom in and it looks more and more linear. And so this brings us to the notion of a tangent line. Before I talk about that, one way of kind of imagining what we're doing here, and if you don't like this approach, you don't have to, so you can just forget it now, but some of you might prefer this idea. Before I talk about the tangent line, which is going to be a little bit awkward, what you might imagine is when I say I zoom in and I look at kind of this, the area around a point, and it looks more and more like a little line. Really, you could do this around any of the points, right? So you can kind of imagine this function as being broken up into infinitely many, infinitely small line segments. These kind of like little straight line segments. You're approximating the actual smooth curve by this kind of choppy, piecewise linear thing. This thing that's built up out of lots of little lines. And you can say, all right, well, as long as I'm only interested in what's going on around that point, I can use maybe this point over here. I can just use that kind of linear approximation. It's not exactly equal to the function, but at least as long as I'm only interested in what's going on around that point, it's not a bad approximation. Okay, but so I mean, what would the graph or the equation of one of these lines look like, these tiny little line segments? Well, it's easier if we don't draw them as tiny little line segments. It's easier if we just take that one line segment that we're interested in, but you know what? We just kind of extend it to be a function over the entire plane. All right? So this is what we call the tangent line. So this is the line, and let me write it nice and proper. This is the line tangent to the graph of our function f of x at the point, and I'll give you the x and y coordinates here. The point is a, that's my x coordinate, f of a, right? At the point a, comma, f of a. And what does this word tangent mean? Well, it means it's a line, and it means that it hugs this curve, the graph of the function, as tightly as you could possibly do it. It's the best linear approximation. So that's kind of what the word tangent means. When I say it's tangent, that means that it is the best, and I certainly don't want to make the word best rigorous, so you just take it for granted. It's the best linear approximation. So linear approximation, it's a line, and it approximates the function at that point. At the point a, comma, f of a. And how can I convince you that, hugging the graph in this way, going with the flow of the graph, is going to give me the best linear approximation? Well, here's why. Imagine if I drew this line instead. That's a very ugly approximation, right? What about this line? It doesn't look like the function at all. And actually, if we draw what these tangent lines look like as we zoom in, what does the tangent line look like here? Okay, that actually looks pretty decent, right? It's not that bad approximation. The full red line here is a horrible approximation to this black curve everywhere aside from around that point A. I mean, it's a pretty awful approximation out here. Out here, it's wretched. But over here, it's actually not so bad. And if you keep zooming in, what does it look like now? It kind of looks, I mean, man, after a certain point, you keep zooming in, you can barely tell the difference between the graph of f of x, the thing that we're actually interested in, and this tangent line. So all of this business about derivatives that we're going to talk about, or the differential calculus, has to do with figuring out what the equation is for this tangent line. So first of all, let's talk about this. How on earth are we going to find the equation for this tangent line at the point a, comma, f of a? Let me just erase some of this nitty-gritty stuff away from that. How are we going to find the equation of this best linear approximation, or this tangent line? Okay, well, how do you find the equation of a line in general? You're going to use the point-point formula, or you're going to use the point-slope formula. And actually, I don't know any of these other points that it touches necessarily, so point-point probably isn't a good idea, but it'd be really great if I could find the point-slope formula. Right? The point-slope formula, remember, is if you know that it passes through the point a, comma, b, and it has a slope of m, then the graph is just given by y minus b over x minus a equals m, right? That's the rise of an arbitrary point over the run, and that should equal the constant slope, m. So that's the graph of a line. But I need to know a point that it passes through, and I need to know the slope. Well, as far as point that it passes through, I actually already know a point that it passes through. Take my b equal to f of a. I know that it passes through this point on the graph of the function, a, comma, f of a. So I have my point right away. So the real difficulty, and this is what we're going to do in the class and spend most of our time dealing with, the real difficulty is in figuring out what the slope of the tangent line is. Because once we have the slope, we already obviously have a point, then we'll be able to find the equation of this tangent line. So we'll have the equation of the best linear approximation. And that'll be great. That'll tell us a lot about this function, at least in a small neighborhood of this point A. And of course, for different points A, you would have a different line. And so you'd have to find the equation for that. But you can do that for just about any A. Okay, so I just want to do two more things before I end this video. First thing is I want to talk about, does every function necessarily have a best linear approximation at every one of its points? And the answer is no. So let me just offhand draw a graph for you. Suppose you have the absolute value function, but maybe I've shifted it so that its little corner is right there. If this is my point A, this is my point f of A, and I want to look at the best linear approximation here, well now if I zoom in on this little V that I've got going on there, guess what? It still looks like a V. And it doesn't matter how often I zoom in. If I can keep zooming in as much as I want, no matter what, it's always going to look like a V, right? So it's never going to look like a line. That was the point. That was the goal of what, the idea of what really made this work, that you zoom in and it looks more and more like a certain line. Here, there is no line. No matter how much you zoom in, it looks like a V. So things with corners don't have a best linear approximation. So they don't have a tangent line at the corner, by the way. At the corner. It certainly has a best linear approximation at some point that isn't the corner, like that point over there. I mean, what's the best linear approximation? It is a freaking line over there, you know. Or, you know, this doesn't have to be a perfect linear corner. It could just be kind of like a cusp corner, like this, or something like that. So here you'd have a tangent line. Here you'd have a tangent line. Most of these points are nice, except here, no matter how much you zoom in, you're always going to get this kind of curvy corner. So things with corners, be they straight corners or curvy corners, don't have a best linear approximation at the corner. Okay, so I better finish this video up because I'm running out of battery life. Alright, so that's one of the things I wanted to point out, that you don't always have a best linear approximation. We'll spend more time talking about when you do and when you don't. But I'll go back here to my original example. Remember, the slope of this line, because the graph was representing the distance you traveled during your jog as a function of time, the slope was interpreted as the velocity that you were traveling at. So here, if we look at this function, this nonlinear function, what it means is that your velocity is changing. So we can't talk about the velocity you're traveling at during the entire jog because it's changing every second, you know. But what we can do is we can approximate it, let's say like these little lines again, and we can say, hey, you know what, at this time, at that time t, you can approximate your graph. You are pretty much almost going at a constant pace, right? As long as you only look at, maybe that's exactly 3 seconds into your run or 3 minutes into your run. If you look at what was going on from 2 minutes and 59 seconds into your run and 3 minutes and 1 second into your run, guess what? I doubt there's going to be that much of a difference, right? The speed you are traveling here, here, and here are probably going to be just a tiny bit different, but just a tiny bit. I mean, they're going to be almost the same. So that's why you can kind of approximate by these tiny like little linear pieces. And you can say that, you know what, you're instantaneous. At that one instant, your velocity was equal to the slope of this little kind of linear piece here. Or, if you like, it's the slope of your tangent line. So there's another reason that we're interested in the slope of our tangent line. Not only do we need it to plug into the point slope formula to actually figure out the tangent line, but in case the graph of the function actually has some kind of physical meaning, like it should represent the distance that I'm traveling as a function of time, then the slope at any given point is going to represent the velocity that I had at that point. So velocity at time A. And it changes with A, as you would expect, because here I'm going backwards, it's a negative velocity, and so on, and I slow down at some point. And just finally notice that if the graph happens to look like that, well, what does it mean up here? Here, at this like apex, my line has a slope of 0. So that means that what? It means that I've stopped. My instantaneous velocity at that point is equal to 0. It's equal to the slope of the tangent line at that point. So that's all I want to say. I'm running out of battery. We'll talk more in the next video.